I've been interested in science ever since I was a toddler and was pointing at a picture of a dinosaur in a book and going, monster! Anyway, but there's a big problem with the way we teach science. We teach it as a body of facts, and that encourages many people to think of it as just another sort of dogma. And that's not at all what science is about. What we don't teach well is that science is a process. Think of it as an error correction mechanism that kills off bad theories that fail their reality test. We gain confidence in a theory when it has survived many battles with observation and experiment, any one of which could have killed it off. This is quantum mechanics after the aspect experiment. So they gave it a good beating, but it was still standing when they were done.
That's quantum mechanics.
Awesome.
So tonight I'm going to give you a taste of science as a process by following the development of astronomy, from the ancient Greeks up to Newton. Now, nowadays it's no mystery how we know the world is round. I mean, we've set spaceships around it. We've gone out. We've looked back and taken pictures. It's no mystery how we know so much about the planets and their orbits. I mean, we sent men to the moon. We sent robot probes to Mars and Jupiter and all of the planets, in fact. But how did the early astronomers, who lacked all of this technology, how did they figure all this stuff out without ever leaving the ground? That's the story I'm going to talk about tonight. Okay, try to give you a bit of an appreciation for how hard won this information was, and just how much they knew how early. It really surprised me. So let's start off with the shape of the Earth. So when did they first know that the world was round? Was it when Magellan did his voyage around the world, 1519 to 1522? Or how about further back, Columbus? You know, the usual story that we're told is that Columbus thought the world was round and everybody else thought he was crazy that it was flat. And that's wrong. That's not the true story. The true story is that Columbus was wrong. He thought the world was considerably smaller than it actually was, and he thought Asia was considerably larger than it actually was. And everybody thought he was crazy because he had his numbers wrong. They thought he was going to starve out in the middle of the ocean before he ever got to Asia. Turns out, Middle Ages, nah, they knew the world was round. And in fact, they had a pretty good idea of how big it was. Pretty much anybody in the Western world knew this. Rome, Cicero and Pliny and their writings take it for granted that the world is round, and take it for granted that their audiences know it also. Historians said that after 400 BC, no Greek writer of any repute thought the world was anything but round. And Strabo, a Greek historian, speculates that the seafarers in Homer's time, you know, the author of the Iliad and the Odyssey, 850 BC, probably already knew the world is round, because there's a line in the Odyssey that hints at that. So how do they know this? I mean, 850 BC or 400 BC or whatever, I mean, that's a long ways back. I mean, so let's imagine you live in ancient times, okay? Forget all the photos and videos from space you see. Forget all the astronomy you've learned. Forget Cosmos. Forget Nova. All you know of the earth and the heavens is what you can see for yourself and the accounts of travelers. So how in the world would you ever get the idea that the world was round?
Would it possibly be, you know, if you're up on, you know, the crow's nest of a ship, or
we're
you
gonna
know,
get there, yeah.
that sort of thing? Just observation,
We'll
mostly?
see. It turns out that the clues are all over the place.
The moon. The moon is round, and the shadow on the moon in certain phases is not straight.
Right.
You know, it curved. That would be, for me, the biggest clue, because I'd never be in a crow's nest out in the middle of the ocean.
So I'm going to start off with a fictional scenario. We don't actually know exactly how they found out. We know some of the things that various writers talked about when they explained why the world was round, the reasons they give for why one should believe this, but we really don't know exactly how they figured it out. We know that Plato said he thought the world was round, but he didn't really give very good reasons for it.
How did the Egyptians know much? Do we have any record
I
of that?
don't know of any as far as I can tell, the Greeks were the only people who figured this out. And, you know, everybody else learned it from them. So, I'm going to do a fictional scenario here. This is not something that I know of that happened, but something that could have happened. It's a very, very simple way that you can figure out that the world is not flat. Okay, that pretty much anybody in those days could have done. So let's suppose that you live in a Greek colony, maybe it's 500 BC or so, and one day you're out watching the sunset, and right after the sun goes down, you turn around, and as usual, you notice that the mountain behind you is still lit. And you watch for several minutes, and you watch as the night line creeps up the mountain. And suddenly you really realize something. You can use this to measure the distance to the edge of the flat Earth. And being having a good Greek education, you know your geometry. So here's the idea. First of all, to keep this simple, all right, we can do this even if this isn't true, but we'll assume that you're someplace where the sun is going down due west, right? So it's going down straight. It's not going down like this, right? So you're out near the equator or something. But like I say, the math just gets more complicated if you're not there. So if the sun is very, very far away, these lines are essentially parallel as the sun goes down. This is what it is at when you see the sun go down. But the mountain's still lit. And as the sun goes down, there's a point where finally the top of the mountain is in shadow. And this angle here, you can figure out that angle by measuring the time. Okay, it's going to be about 6 minutes or so. And you can get that angle because you know that the sun does a full 360 degrees in 24 hours. So if it takes 6 minutes for that night line to reach the top of the mountain, then it's going to do 6 minutes divided by however many minutes are in a day. That's what fraction of the circle is. Mm-hmm. Now once you know this angle here, that's the same angle here. Okay? And if you know the height of this mountain, you know this angle and you know the height, you know this distance here. That's either you know it because you know trigonometry and you look it up. You look up the tangent in a table, or if you don't know trigonometry, you go out and you draw yourself a big triangle with that angle, and you just measure what that ratio is. Okay? And so, yes, computing it all out, 6 minutes, you work out that that's about 1.5 degrees. It's about 3 sun diameters. And let's suppose the mountain height is 7,240 feet, which that's how high Tempe is above that valley here.
Was there a good way for them to know that, or
Yes,
they'll get there?
actually there is. Now, there's a caveat here. I assume that the sun's rays are essentially parallel. You might ask, what happens if you're wrong, or what if it's close enough that they're actually diverging a little bit? Well, if that's the case, you'll overestimate the distance to the edge. You'll think it's further away than it actually is. Okay. But for the moment, we'll just go with this. So it was a good question you asked. How do you know how tall the mountain is? And it's more geometry,
Okay.
more trigonometry.
Okay.
You basically go out and you measure angles from 2 different distances, and you do some trigonometry, and you get the height at that point.
Yeah.
Okay. So this is great. So you plug in the numbers, and this is going to be a great scientific, you're going to be able to tell how far away the world, the edge of the world is. You can tell people. Maybe you'll send an expedition. People will see it. You're getting all excited, and it's 52 miles away. What? That's what the numbers are saying. That the edge of the world is 52 miles away. What the? Phi Epsilon Kappa. That can't be right. I mean, you talk to traders who've traveled a good 1,000 miles to the west. You know the edge of the world can't be 52 miles away, right? And if the sun wasn't as far away as you thought it was, that says it's even closer. The edge of the world is even closer than that. So at this point, you're not sure what to think, but you know for a fact that the world is not flat. It can't be. In fact, you don't, maybe it's cylindrical, right? You don't really know what the shape is. You just know it's not flat at this point. If you assume it's round, you actually have enough information now. You can even figure out how big it is, what its size is. Okay, and that's just sitting on your porch with a stopwatch.
Interesting.
With a watch. Okay.
So when did they learn about geometry? Yeah, that's Euclid and, you know.
Oh, the Greeks. So by that time, hundreds of years before, hundreds of years BC, the Greek were very good at geometry by that point. Geometry goes way back because it was useful when people were building pyramids and buildings and things like that. So what evidence did the Greeks actually use? And I don't know that they actually used that particular method. I haven't seen that mentioned, but it's one that I can imagine somebody using. You're probably familiar with this one. Ships going over the horizon, watching a ship go out. So this is actually, somebody modern day just went out and just, photographed it, right? So this is a big cruise ship. You see that it's very high in the water. And as it went out, you see that it's getting lower in the water. And a little bit further, it's even lower. And this just shows you about half of it is below the horizon at this point. Now, one of the things that the Greek writers do talk about is ships approaching land. So Strabo, who lived around 81, before and after that time, he mentioned that elevated lights and high lands were visible to sailors at a greater distance. Ptolemy, about 150, mentioned that when sailors are sailing towards a mountain, it would seem to rise up out of the sea. Mm-hmm. And we can sort of see what's happening here. So this dot rock down here is your ship. This is your mountain, and it's just hidden until you get close enough. So if we're talking Mount Temp there, Mount Temp would be hidden at 110 miles. You wouldn't be able to see it, even though at that distance it would look about 1.5 times as wide as the moon. If the world were flat, you could see it, and it would be about 1.5 times the moon. In fact, somebody calculated that if the world were flat, you'd be able to see the Rocky Mountains from Chicago.
Interesting.
Wow.
Yeah. So, you mentioned this one, right? The lunar eclipses. So, Aristotle mentions this as one reason to believe the Earth is round, right? So the geometry says that an eclipse is the moon going through the Earth's shadow, right? It only happens in a full moon, when the moon and sun are opposite sides. And we see a circular shadow as it moves across there, and that's an indication of a circular Earth.
But you don't even have to wait for an eclipse, just the phases of the moon.
Well, that's not the Earth's shadow, though.
But
That's the part of that. That's the night and day side of the moon. So that tells you, and we'll show that the moon is round.
Okay.
Tells you the moon is round, and that certainly might suggest that the Earth could be round too.
okay, and that's the conclusion I would have drawn.
Right.
The way
So-
my brain works.
So this isn't entirely conclusive, because you could say, well, what if the Earth is a round disk? Could it not also produce a round shadow? But there are times when a lunar eclipse happens just as the sun goes down. And if you had a flat Earth and a lunar eclipse happening at that time, that's what it would look like.
Oh, interesting.
All right? And we never see that. It's always round. All right. So there are some other things they looked at. There are time discrepancies. So on a flat Earth, the sun has to rise and set at the same time everywhere. And even though they didn't have the greatest clocks They did have ways of checking this. Basically, they could see, they were aware of this phenomenon. Lunar eclipses also. So people in different areas would what time was it when this lunar eclipse happened? And people to the east would say it happened later in the day, or later in the night, than people in the west would say. And so that's also an evidence of curvature, right? You're not going to get that on a flat Earth, but it's a very natural thing to happen on a curved Earth. Now, this is evidence for east-west curvature, right? It doesn't tell you anything about north-south curvature, but it does give evidence that there's at least curvature in an east-west direction. So there was also evidence in the stars, and again, Aristotle, 350 BC, writes about this, talks about it. So he mentions that there are constellations that are visible in Greece that are hidden below the horizon when you get to Egypt. And vice versa, there are constellations you can't see from Greece that show up when you get into Egypt. And again, that's something that just can't happen on a flat Earth. Right? On a flat Earth, if the stars were close enough, the sky might look different, but it would be because part of the sky would look bigger and the other parts would look, smaller, more distant. But anything that was above the horizon would be above the horizon for everybody, no matter where you were. So this is evidence for north-south curvature now. And so just to illustrate that, so these are some of the northern constellations. You only see in the northern hemisphere. These are constellations you only see in the southern hemisphere. And like Orion here is one you can see in both the north and the south hemisphere. And there's just a diagram that sort of shows the idea, right? So you can see if you're here, anything that's in that, further down, more of a southern direction than that, you're just not going to see from this northern place. Okay. And this was really the clincher. I mean, really, the stars, that's the real clincher for a round Earth. In fact, not just a curved Earth, but a round Earth. Because you can go south, and if you look at the dome of the heavens above you, the stars, the further south you go, like every 100 miles, it sort of like rotates by the same amount, right? A constant amount, which indicates a constant curvature, right? Which you're only going to get if it's actually a sphere shape, at least north-south. Right? So finally, the last thing I'd like to mention about the whole, shape of the Earth business was, figuring out the size of the Earth. So, 240 BC, Eratosthenes. He figured out the size of the Earth because he had found reports that far to the south, in what's now, I guess it's very far to the south of what's now Egypt. There was a city that was, now those days was called Syene. And on a certain day of the year, the sun was directly overhead. There was a deep well. You could look down and you could see the sun, reflecting off the water at the bottom of the well. On that same day, you saw a shadow in Alexandria. And so, if you're assuming the Earth is round, this angle right here is the same as this angle, which is the same as this angle given by your shadow. So by measuring that angle, we got this angle, and then he sent out a servant to walk the distance, a few hundred miles, and find out.
And what, he had a
That's
wheel
how it
that,
was.
did
What's
he
that?
have a wheel that kept track of the distance?
I think it was
or-
just pacing. You I don't know if you've ever, when I in Boy Scouts we did this, right, where you have a known distance and you sort of get your pace in and you sort of figure out how long your pace is, then you can walk a long distance and just try to walk at a
consistent,
steady pace
yeah.
and be consistent and count it off, So then you get the distance, and then once you've got this distance and this angle, boom, you've
got a
the
piece.
circumference of the Earth. 240 BC.
Wow.
And
Didn't somebody else come up with the distance around the same time on a different part of the Earth?
I don't remember.
Seems like I've heard.
It seems like there may have been
Two
other
different
kinds of things that people did. But at the moment I'm I'm drawing a blank.
It seems like in China or some, like in the East.
Well, no, in China, they actually didn't know that the Earth was round until like the 1700s.
Oh wow.
In China?
Yeah. I mean, they did all kinds of other things. They
Yes.
sunspots, and so this is why I say something was really different about the Greeks, because they're literally the only people in the world who figured this out. And I think it's because they were so good at geometry, and they were just so good at abstract thinking. It was just the way they thought about the world.
Soft chairs.
All right. Well, so hey, we've got a round world.
There are no flat earthers left in the room.
It just boggles the mind, you know. These flat earthers out there on
The guy that
on their
blasted
YouTube
himself
channels and
up.
everything. It's like, you guys are literally 2,500 years behind the times. I mean,
So amazing.
and apparently, the flat Earth movement kind of thing didn't even get started till like 100 years ago or something.
Huh.
And there were no flat earthers. There was no flat Earth movement or anything like that in like the 1800s.
There can't be a
The
single
1700s.
mathematician among them. You know, there can't.
What was it? It was like a. I looked at one of these. I literally thought that it was a parody,
Oh,
but he
really?
was serious. This guy was like a well-educated lawyer and everything, but I just could not comprehend how he could.
Yeah.
Wow.
Anyway, so let's move on from there. The Greeks didn't stop at figuring out the shape of the Earth and the size of the Earth. They figured out quite a number of other things about the sun and the moon. So I think we already mentioned a little bit about this, the shape of the moon, by looking at the phases of the moon as it goes around the sun, or the sun shining on the moon, lighting it up. You can see that curvature, strongly suggestive of a round moon. Now the next thing, we're going to see how they actually figured out how far away the moon was. And to get there, let's first talk about angular size. Okay, so if you're talking about how big something looks, not how big it actually is, but how big it looks, right? Its apparent size. What do you measure that in? Well, you measure that by the angle, right? If you think of a big, huge circle, how much of a circle going around your head does it cover? Okay, so the sun and the moon have an apparent size of half a degree of angle. So that's what we refer to as angular size. And I just plug this back in again. And the thing about that is so we're all familiar with the idea that, right, if you have two objects, one's twice as wide as the other, but it's twice as far away, they're going to look the same size. It's going to have the same apparent size. We see that with eclipses. The sun is much larger than the moon, but it's also much further away, and so they have the same apparent size. They have the same angle in the sky. And the important thing here is that if you know this width here, and you know this angle, you know that distance, right? So, for example, if I had a big banner that I knew to be 10 feet, or a big orange pole that I knew to be 10 feet tall, and you carried it far away from me, I could know how far away you were just by measuring the apparent size of that, right? But you can turn around. So we've been thinking about your eye. Your eye is here and the object is over here. Well, let's turn it around now. Let's have two observers on the other end, separated by a distance, and they're looking at this thing over here. The same logic still holds. You know the distance between these two observers, and you know the angle. They're looking at slightly different angles to see it. You know how far away that thing is. This is called parallax. And this is used over and over and over again. We'll see this over and over again. This is just a wonderful method for finding out things that are far away that you can't possibly actually reach. Okay, so Aristarchus, 270 BC, he figured out the distance to the moon. And the way he did it was he timed how long it took during a lunar eclipse, so a full lunar eclipse, at one that had maximum time, how long it took the middle of the moon to move through the middle, to cross through the middle of the Earth's shadow. Okay? So what that told him was, let's see, how do I want to see this? It told him how far away the moon was in multiples of this width here. Okay, so at that point, so even if you don't know just how wide that shadow is, at least you know how many times that width it is that
Yeah.
distance, right? Now, you'll notice that you expect that shadow to be about the width of the Earth. And he did know the width of the Earth. He knew that was 8,000 miles. But there's a little bit of this happening because, well, I'll show you the next slide. Right, because the sun's big, right? Because it covers half a degree in the sky. So I won't go through the details. He did a whole bunch more geometry involving, figuring out the different angles were the same and the different angles summed up to 180 degrees and everything. And he was able to figure out what this was as a fraction of the Earth's diameter. So once he did that, he knew how wide that shadow was. Once he knew how wide the shadow was, he knew how far away, and he knew that angle. He knew the angle. What? So why did he know the angle?
Which angle?
Let's go back to the slide. This angle here.
Because he
Okay.
measured the time it
He
took.
measured the
Yeah,
time,
so-
and he knew how long it took
Yeah.
the moon to go around once.
Yeah.
So he knew what fraction of a circle that was. Right?
Yeah.
So 270 BC. They already know the moon's 240,000 miles away. Yeah, it just boggled my mind when I first realized some of these things, just how much they figured out. Okay.
And so what time frame was he when he
270 BC.
struck us? Okay.
Yeah, that's Aristarchus. Hipparchus in 129 BC used a different method to find the distance. So, multiple methods. Some methods get more accuracy. He used parallax. So what he used was a total eclipse of the sun this time, not of the moon, but of the sun. So in Hellespont, you've got the Mediterranean here, and you've got the Black Sea here. The Hellespont is in that that region of that narrow passageway between the two of them. The Hellespont, I don't know if I'm pronouncing that right. Seen from there, the eclipse was a total eclipse. But down in Alexandria, it wasn't total. It only covered about 4/5 of the sun. Okay, and so he was able to get the distance between these two from their latitudes. And he did have to make a little bit of correction for the fact that the Earth was curving in between there. And anyway, angle, distance between observing points, you get a distance. And
They had good records, I get, because you can't talk to them simultaneously.
I don't know whether he talked to people after the fact or whether
Yeah.
he set it up beforehand.
Huh. Could they predict eclipses?
At that time, they couldn't.
Yeah.
I think that would have been maybe after Ptolemy.
Okay.
I don't know that they knew enough to be able to predict an eclipse at that time. I'm not sure, though, about that. But anyway, yeah, you get about a 0.1 degree of parallax difference. Now, as we'll see in a second, one of the things that makes this work is that the sun is much, much further away than the moon. So there's no significant parallax with the sun. And he knew that the sun was much further away because of another thing that Aristarchus did, which we're going to talk about now. So Aristarchus not only figured out the distance to the moon, he figured out how much further away the sun was than the moon. So he got a distance to the sun. And it's very clever the way he did it. So think about the phases of the moon as it goes around. Okay? When it's on the opposite side of the Earth from the sun, you get a full moon. When it's on the same side, you get a new moon. And when it's halfway between, you get the half moon. Except Well, that's what you get if the sun is infinitely far away. It's actually at a finite distance. So you actually get the quarter moon at a point that is a little bit, sort of angled inward. And so he tried to measure very carefully what this angle here was. And he concluded that it was 87 degrees. Now he was wrong. His measurements were off. And he didn't really know how to take into account, measurement error. And the actual number is like 89.83 degrees.
Wow.
It's very close to 90
Yeah.
because the sun is very, very far away. Okay? But based on the 87 degrees, he estimated that the sun was 19 times further away than the moon, which would have put it at 4.5 million miles, which still is like, yeah, we're used to hearing numbers like that nowadays, but just imagine that you're back there, hundreds of years BC, and like, that's 5 million miles away. That has to have just been been mind-boggling at that time.
Did they use the miles measurement?
No, they didn't use miles. No. But also, if you know the distance to the sun, of course, because you have its angular measure, we do the parallax thing only in the other direction. Now we know how wide it is. And so again, he thought it was much closer than it was. He came up with a figure of it being about nearly 5 times the Earth's width, which it was a gross underestimate, right? Because he got that this number of 87 degrees was wrong, but still was like, oh, the sun's a lot bigger than the Earth, and that actually caused him to think about a heliocentric model. The sun at the center and the Earth going around it because of that. Although I didn't get any traction with that. Nobody seemed to pick up on that idea. Anyway, over the next 2,000 years, various people sort of refined this method and got better measurements. And using this method, they got within the 3 to 4 times the true value. So still not very accurate, but at least they got closer to the right number using this. And you can see why it's not going to be very accurate, because it's a very small deviation from 90 degrees. It's really hard to measure that well. All right, well, so that's the ancient Greeks who've got the moon, the size of the moon, an underestimate, but still they know the sun is a long ways away and it's really big. And anyway, after all these successes of Greek science, I guess it was inevitable that mistakes were made. So we've talked a lot of good things about what Aristotle did up to now, but now we're going to talk about all the things he got wrong. You're going to kind of get beat up on a bit here. He contributed a lot even outside of astronomy. He basically invented logic and a lot of other things too. But sorry, Ari, we're gonna point out all your mistakes now. So let's do an inventory of the heavens. Looking up into the skies, what do we see? Well, we see the sun, we see the moon, we see the fixed stars, and we see these nonconformist wandering stars, the austere planetes, that were named after the gods Hermes, Aphrodite, Ares, Zeus, and Kronos, or as the Romans called them, Mercury, Venus, Mars, Jupiter, and Saturn. And nobody really knew what they were, but they were, not only did they wander, but they had quite noticeable disks. If you really look, if you go outside, you'll notice the stars twinkle. The wandering stars don't. They have a much more steady light. And so Aristotle, did his first guess at, what was going on here. What were these? How were things set out? And so here's his cosmology around 350 BC. He had everything circling the Earth, the moon closest, then Mercury, Venus, and then the sun, and then Mars, Jupiter, Saturn, and then this outer shell that had the fixed stars on it. And so he had this notion that the Earth was corrupt and imperfect, and the heavens were place of perfection. And so he thought that they should move the heavens, they're very unchanging compared to the earth. They're very regular. So he tried to fit everything into this unchanging circular motion. Perfect circles, the rotation always the same, never changing. He had this notion like 53 different concentric crystalline transparent spheres that the planets were on, moving around. The moon itself, here in the closest, you notice was the closest to the earth. That sort of marked the boundary between the unchanging constant heavens and the corruptible earth. And that explained why you see these blemishes on the moon, right? You see these kind of dark spots. It made sense at the time. What can I say? It doesn't make sense to us, but again, all you know is what you see looking up at the sky, right? You've not. You got to give him.
Regardless.
It's you got to work with the information you have, and he just didn't have all that much information. And he had some again, based on what they knew in those days, these were pretty strong arguments against a heliocentric model, meaning a model with the sun in the middle, with the planets and Earth going around it. Okay. The first one was, what would push the Earth? We observe that the Earth and things on it seem to be composed of these heavy things, substances, whose natural state seems to be rest. Right? If you're not pushing something, it stops moving. Unless it's falling. It requires force to get them moving and force to keep them moving. By the way, any Star Trek fans here?
Oh yeah.
So this is why the Enterprise falls out of orbit if its engines fail. Because you can't keep moving if you don't keep on running your engines, right?
Never caught
Did
that.
they ever observe the other planets and come to the conclusion, well, they're orbiting, why can't we orbit?
Well, they were figuring that out, but see, what they thought, though, was they really thought of the heavens and the earth as very, very different regions with completely different laws. Nobody at this time, and for a very long time, expected the same laws to apply up in the heavens as applied here on the earth. So they had this notion that, whereas things on the earth are made of this stuff that doesn't want to move, stuff up in the heaven, its natural state is circular motion. Perpetual circular motion. Okay.
So, I guess I'm a little confused. So they came to the conclusion that things on Earth needed forced upon to be moved, but things in the heavens did not.
That's right.
Okay.
Right. And even though we now know better, this whole business about you have to push things to keep them moving. That actually does describe what happens when you're moving through a fluid like air or water. Right? If you jump out of an airplane, you will not accelerate indefinitely. Okay? You will hit what's called terminal velocity. As you're going faster and faster, the air friction will get greater and greater, and you will hit terminal velocity. And then you will just go at a constant velocity until, well, there's a reason they call it terminal velocity.
So which is why when you're in introductory physics, you've got to talk about like a frictionless environment, and you have to do all these things you don't actually see in real life.
That's right. And so you can imagine that it took a while to sort of tease all that up because friction really gums things up, so to speak.
Mm-hmm.
All right. So there's this idea that the Earth is huge. Something's got to push it. It can't just go on its own. And if the Earth was going around the sun and the moon was going around the Earth, well, how is the Earth dragging the moon with it? It's just nobody had any idea how that could possibly be true. Another argument was the consistency of Venus's luminosity. So if the sun were going around Venus, then you would expect that when it was closer to the Earth, it would be brighter. When it was further away in its orbit around the sun, that it would be dimmer. But we actually see it at pretty much the same brightness all the time. But finally, the real major argument, and this is the real, this was a complete showstopper, was the lack of stellar parallax. Okay, so we talked about parallax. If the sun is here, and the Earth is going around it, we should see some parallax, just from one side of the Earth's orbit to the other side of the Earth's orbit, we should see the stars shift. And nobody saw that. So, he had good reasons for rejecting a sun-centered model. Okay, it wasn't that he was dumb. He had really good reasons based on what they knew about those things. I mean, you have to make, you can't do better than the information you have.
So they measured the apparent degrees between stars, and based on, if they are on one side of the sun versus the other, those apparent degrees would be altered.
You would expect that you would expect to see, you'd expect to see some sort of changing, a little bit of a changing position in the sky if that's the case.
But the stars were just too far away for them to see the alteration.
Well, actually, I'm going to ask you to hold off on that because I still want you to have the mindset of you don't know all this stuff yet.
Okay.
Right?
Jumping ahead.
I want you to pretend that you're still there in ancient Greece there, and you don't know about any of that. I mean, yeah, you could say they could be very far away, but they'd have to be extremely, just unbelievably far away. I mean, think about, already they knew the Earth's orbit had to be at least 10 million miles across, right? And to have no parallax, the stars would have to be immensely further away than that, and that just seemed crazy.
Probably
Yeah.
terrifying.
Yeah.
All right. Well, so Aristotle's model actually didn't do all that great of a job of predicting actual motions, and there were various refinements that happened to it. So Hipparchus, in 150 BC, he noticed that the seasons don't have the same length. So spring is when, we've got the equinox. Start of spring is, and start of fall is the fall equinox, and then the solstices, the summer and the winter solstice. And so if the sun were going around the Earth in this circular orbit, you'd expect those to be equal length, right? But spring was about 92.8 days, summer was 93.6 days, different length. Autumn was 89.8 days, winter was 89 days. They weren't quite the same length of time. And so he tried to figure out how to fix this. He actually considered a heliocentric model, but he dropped it when his calculations showed that he couldn't get perfectly circular orbits. There was still this notion that the heavens had to be perfect. Anyway, what he did is he said, well, let's say the sun's going around the Earth, but its actual center of its orbit is actually offset from the Earth. It's not quite centered on the Earth. And that was his solution, and that got it a little bit better. Still wasn't enough. So they played with doing things like adding things that are called epicycles, which I'll show you in a second. And the epicycles are there because of this problem of retrograde motion. So if you follow the orbit of the path of Mars to the sky, okay, and after we take out the daily rotation of the sky, with respect to the distant stars, you see it do this backtracking business at some point. It goes and then it backtracks and it continues on. How in the world do you explain that?
And that's why they call them planets, right? Wandering.
Well, not that. This isn't the only reason.
Okay.
It's because the fixed stars just stayed in one place.
Okay.
And so this is where the epicycles came from. That if you said, okay, this planet is going in a circle, well, actually it's not. It's going in a circle that is centered on a point that is going in a circle around. And that could explain why when this is coming around this way, if it's rotating like this, it's going forward, then it goes back, when it's rotating around this part, and then forward again. That was intended to get that retrograde motion. So this is Ptolemy in 150 AD. He took all the things that people had been working on, and he added one more bit to it. As he said, instead of saying that the motion is uniform, it's actually uniform motion here, the circle here. Let's just say that the angular change is uniform, measured from this other position that's not the center of the circle. So essentially it's moving faster down here and slower up here. Okay? that was his big innovation. And, you know, it got him a pretty good model where they could predict things. They could tell where the planets were moving. That was the best predictive accuracy anybody had ever gotten. And people used that for 1,400 years. It lasted a long time. What did he figure out? He got the ordering, you know, his ordering was basically, you know, like Aristotle's. He figured the stars were at least 20,000 times the Earth's radius is away, about 80 million miles away. He figured they had to be at least 80 million miles away, based on this. Okay, so we have to wait 1,400 years for anything interesting to happen. And along comes Copernicus. Now, Copernicus is usually the hero of the story of the sort of the sun of the, you know, everything that happened this time with a new understanding of astronomy. We'll see that maybe what he did isn't quite as impressive as you might think. Copernicus had some problems with Ptolemy's model. One, he wanted a better explanation for that retrograde motion. He wanted to understand why do Venus and Mercury stay close to the sun. Okay, because, yeah, you observe that. A better explanation. So those are actually good reasons for looking for something else. The other reason for not liking Ptolemy's was that he really didn't like this business. Because he really felt, these are the heavens! Circles! Uniform motion! It has to be perfect! So yeah, he was convinced, like Aristotle, that the perfection of the heavens required heavenly bodies to have only uniform circular motion. But one of the things that it was nice about this is sun-centered model. So he's got, you know, the Earth going around the sun, the moon going around the Earth, everything else going around the sun, is that it does explain this retrograde motion quite nicely. Right? You can just sort of see what happens. Here's Mars, here's the Earth. As the Earth in its orbit is going around its orbit faster. Mars takes about 2 years to go around. And so it's catching up and then passing Mars, and that's when that business is happening there. So it was a good explanation for that. You know, the whole business about the aesthetics of wanting to have perfect circles and perfectly uniform motion was kind of, you know. And so, you know, how do we compare this to the Ptolemaic model? Well, it had the sun in the middle. It does provide the relative distances of the planets, which Ptolemy's model didn't. You know, it had the planets at different. His model, you could make the planets at just about arbitrary distances, and it didn't change anything. But with Copernicus's model, right, you had to get the distances, actual relative distances from the sun right. He also included the revolution of the Earth to account for the apparent rotation of the stars in the sky. The tilt of the Earth's axis. So these are all really good things that he did with his model. These are the plus sides, things I think he got right. He of course had to assume the stars were very, very far away, much further away from the sun, because otherwise you'd get this parallax. But you know, everything had to be a perfect circle, and he had to have epicycles because he couldn't get it to fit the data without sticking it in his own epicycles. And he had to play the same trick of making the circles be off-center, offset, you know, from the sun. So he had to do all those. So in the end, you know, it had some advantages, but it wasn't really any more accurate than Ptolemy's model. And, you know, based on what was known in his day and age, all those objections that Aristotle had to a heliocentric, sun-centered model, those objections still stood. Mm-hmm. He didn't really have any answer to those objections. Well, there were some developments that occurred in the decades after that began to erode this idea of perfection of the heavens, this idea of the heavens as being unchanging. Okay, so first of all, the astronomer Tycho observes a new star, a stella nova, which is actually supernova, exploding star nowadays. Okay. But that just means new star. Okay, and because there was no daily parallax, meaning that, you know, as the Earth rotates, you should expect to see a different angle from one side or the other. He concluded that it was really way past the moon. It was out in that region that was supposed to be the unchanging eternal heavens. And here was something that changed. A new star that wasn't before. Comets had been thought to be atmospheric phenomena. Now in those days, atmospheric meant anything out to the moon. Okay, so that was all considered the part of the Earth. But again, by doing parallax, looking for parallax that should have been there, no, he concluded no, it's far past the moon. It's again out of the unchanging heavens. We've got this comet appearing and then going away after a while and changing. And same thing with another astronomer by the name of Rothman. Another thing that happened was the, I don't know why I don't have that here, but, oh, never mind. Yeah, observation of sunspots. Okay, that happened a little bit later than this, but sunspots come and go. And so the sun itself was changing. It wasn't this constant, never-changing, eternal thing that they had always thought it was. The next big development was the work of the most important astronomer that, well, I don't know, how many people in here have ever heard of Tycho Brahe?
I just know that his nose
They had a nose, a metallic nose. This is the most important astronomer you've never heard of. Okay, he was extremely important. He died in 1601. The first telescopes were invented in 1608.
Oh, man,
He was just a little bit too early, but he was the greatest of the naked eye astronomers. Okay, and one reason he was the greatest is he was obsessive about getting better measurements, better data. These years, 1572 to 1601, are basically his working years as an astronomer. He was born a few years after Copernicus published his model. He was a Danish astronomer. As a teenager, at age 16, he observed that the conjunction of Jupiter and Saturn and saw that it didn't happen when it was predicted, that the predictions were off. And he concluded that, we needed better observations, we needed better data. And he set that as his life's work. And he got funded by the King of Denmark. And he set up this whole big research institute and he had naked eye instruments, right? But he did things to make sure that they were very steady. Like he had them actually embedded in the bedrock to keep them very, very steady, okay? He made improvements on instruments like the sextant and quadrant. These are ways of, again, naked eye observation for measuring angles in the sky and so forth. And he ended up getting observations that were 5 times more accurate than anybody else had ever done. This was extremely important because a lot of later developments really depended on Tycho's work, on his observations. This is often the case in science, right? You get better data, suddenly things start happening. To get an idea of how important he was, the most prominent crater on the moon is named after Tycho. It's Tycho crater. Now, Copernicus has a nice little crater up there, but it's nothing like Tycho's crater. So what did Tycho think about Copernicus and his model? Well, Tycho thought it was really elegant, but, what makes the Earth move? And what about stellar parallax? All those problems that we've been talking about. I mean, we already know that if the Copernicus's model is true, then the whole width of the Earth's orbit has to be like as nothing compared to the distance to the stars. And it gets worse, because when they would look at the sky, it appeared they thought they could actually see, a disk for the stars, very, very small, actually visible width, and they could measure that width. And he did some computations based on the fact that there was no parallax and concluded this is the sun, this is the size of the average star.
Wow.
They had to be enormous, at least that big. That's a lower bound, at least that big. It was just ridiculous. It was like, and if the stars were like, and there had been ideas that maybe the stars could be like other suns, but like, what, the universe is full of these giants, and there's just, our sun's this little pygmy that says the odd man out. And that didn't make sense. So how did Copernicus's defenders respond to this? So this response is not Copernicus himself. I'm not sure if Copernicus was even still alive at this time. But this is what Christoph Rothman replied, who was a prominent Copernican in response to this. You just have to read this, it's great. These things that vulgar sorts see as absurd at first glance are not easily charged with absurdity, for in fact, divine sapience and majesty are far greater than they understand. Grant the vastness of the universe and the size of the stars to be as great as you like. These will still bear no proportion to the infinite Creator. It reckons that the greater the king, so much greater and larger the palace befitting his majesty. So how great a palace do you reckon is fitting to God? So yeah, he played the God gambit. the God did it. So yeah, there was a lot of this stuff going on. So the usual picture we have of this is like the Copernicus and his followers were the scientists and everybody else were religious superstition. No. Everybody had religious superstitions. I mean, both sides were making religious arguments on this whole thing.
It's fascinating, though, that they could get past that to a great degree because of math and because of the science they were doing.
Yeah, the reality checks.
They were slowly learning that there was a problem with one theory or the other.
Yeah, and that's all about that business about, what only the strong can survive. And this is the nice thing about this whole business with the astronomy, and maybe this is the reason that this is where, modern science really took off from, was because it was all about the data, right? Every theory could be immediately checked against the data. So anyway, with all these considerations, Tycho proposed the geoheliocentric model. He tried to get the best of both worlds. So that there were, good reasons for thinking that. So basically, he said the moon goes around the Earth, the sun goes around the Earth, everything else goes around the sun. That way, he didn't have to deal with the parallax problem. He didn't have to, he didn't have to figure out why the Earth could move or anything like that. Well, then right after Tycho dies, things start heating up. Interesting things start happening. It's like, oh man, you really wish that guy could have lived a little bit longer or something. But 1608, telescope is invented. 1609, Galileo and Harriot point the telescope to the moon, and guess what? Looking at the shadows of the moon, we see that there are mountains and craters. The moon is not perfect. It's a lot more like the Earth than we thought. So again, we're eroding this concept of perfection in the heavens. Galileo and Harriot observed some sunspots, more imperfection. The sun is marred also. Galileo, same year, observes the moons of Jupiter. Hey, not everything orbits the Earth. If Jupiter can have things orbiting it, maybe the sun can have things orbiting it too. It also resolves, well, it doesn't entirely resolve the question, but this question of how could the Earth be dragging the moon across the heavens? Somehow Jupiter is dragging its moons across the heavens. So if Jupiter can do it, maybe the Earth can too. Again, same years. Phases of Venus.
How good were the telescopes that they had?
The first ones were like 3 times. And he worked on making them better to like maybe 8 times. And so, I mean,
Not a lot.
not a huge amount, but even that was enough to make a huge difference.
Like a Walmart telescope.
Yeah. So phases of Venus. Think about phases of Venus, they only make sense if Venus is orbiting the sun. And they explain that whole business with constant luminosity. So this is modern observation, what the phases of Venus are. So here, Venus is to the side of the sun, but it's further away from us. So more of it is lit, but it looks smaller because it's further away from us. And as it comes this way, we get more and more of a crescent, but it's also larger in our view. And so it kind of washes out between the two of them. And
That's
again,
why it stays a constant
yeah.
luminosity, even though.
And this whole business right here, right? That whole phases business, you're not going to get that. You can't get that any way other than the Venus orbiting the sun, right? That's the sun lighting it up. And there's just a little diagram of what's going on there. It shows the same thing. Okay. Well, another development happens at this time. This is where Tycho's work really paid off. Okay, so it's just a shame that he didn't get to live to see this happen. Tycho hired Kepler, Johannes Kepler, as his assistant in 1600. So Kepler was a 28-year-old school teacher from Austria, and specifically to help try to make sense of this data and get a better idea of how the planets work. This was an incredibly fortuitous career move, because the next year Tycho dies, and essentially Kepler inherits his data. I mean, it's like he's now sitting on the biggest and best collection of astronomical data that anybody has in the world. You know, at 29 years old. And he goes to work on it and starts trying to come up with better models. And, you know, he was a Copernican and he really wanted those nice circular orbits and the uniform motion. But he just tried and tried and tried, and he just couldn't make it work, no matter how many epicycles he did, and how he shifted the center of the circle or any of that stuff. Especially Mars. Mars was a real problem. Mars was just a troubler. So finally he said, he gave up. And said, let's try ellipses. So an ellipse is sort of like a stretched out or squashed circle. And so here, there's just a little bit there. I mean, these are close to circles, but there's a little bit of stretching out. This is the orbit of Mercury. The dots are what would be a perfect circle. The Earth is very close to a perfect circle. Mars, you know, it is closer to the sun on this side, further away that. So it's stretched out a bit. Let's try ellipses. And suddenly things started working. And you didn't need epicycles. And you didn't need to do weird things where you took things off the center or anything. And what he did is, an ellipse, the center of the ellipse is not at the sun. Instead, what he found, what fit, was that it was one of the foci of the ellipse. So ellipse, a circle has a single center, and all the points on it are equal distance from that. And that ellipse has two foci. So any point on here, if you add together these two distances, they add up to the same number. Okay. And so what he found is that if you put the sun at one of those foci, it all worked. Yeah, you got a very, very good fit to the data. Now this is, of course, grossly exaggerated, right? And none of the planets have orbits that elliptical. Comets do, but none of the planets do. And so, crunching through the data, he discovered 3 laws, Kepler's laws. The first, all planets move in elliptical orbits with the sun at one focus. The second is that it had to do with how fast they went around their orbit. So a line that connects a planet to the sun sweeps out equal areas in equal time. So here's what that means. So we've taken this ellipse and we've divided it up into 13 parts. Okay? Each of these parts has equal area. This and this have the same area. This is longer but thinner. Right? And what he's saying is that this planet will move this distance the same amount of time it moves this distance here. So essentially, it moves faster when it's closer to the sun and more slowly when it's further out away. Okay.
Yeah. And that's why our seasons are different.
No, actually, because the Earth is almost entirely
It's
very, very
round.
close to a circle. It's orbit. It's because of the tilt of the Earth.
Okay.
The tilt of the Earth's axis, yeah. The other one he came up with, and it took another 10 years for this one, he said is that if you look at the period, how long it takes to go around the orbit, that if you take that time and square it, that's proportional to the cube, the third power of the distance from the sun. And what we mean by distance is this, what they call the semi-major axis. Okay. Anyway, so now he not only could, he had the simple rules. He didn't have this big complex mechanism with these arbitrary numbers thrown in, right? He had simple rules that just said, this is how it all works. And this was like, wow, right? Much, much simpler explanation. Everything following from these few simple rules. Well, I don't think I actually need to say that. So one of the things that Kepler system does, it tells you the relative distances of the planets. Because once you know their orbital period, how long it takes to go around, you can use that third law to figure out how far away they have to be from the sun. But that's only relative distance, right? You know that Mars is maybe 1.5 times as far away as the Earth or something. But you don't know how far away the Earth is from the sun. So Cassini, we're jumping ahead 50 years here, later on, sized the solar system, again with our good friend Parallax. Okay? So he was in Paris with Jean Picard, no Lucanville, another. And he sent his co-worker, another astronomer, to French Guiana. And they took simultaneous observations of Mars, set thousands of miles between them. And then they used a parallax calculation to figure out how far away Mars was. And once you knew how far away Mars was from the Earth at one particular point in time, everything else fell out. So how would you choose? So suppose we've now gotten to the mid to early 1600s, and you're seeing all these different models out there. How do you choose which one is the right one? Well, by that time, Ptolemy's model was out of the running. Okay. Nobody really believed Ptolemy's anymore. There were better options. The Kepler's model, it was more elegant, was more accurate than the others. The Copernican model, it was pretty much dead by now because Kepler's was more accurate, right? The Tychonic model, it sort of combined the advantages of the heliocentric and the geocentric. So it was more accurate than Copernicus's model. It avoided the problems with moving Earth. There were no incredibly distant stars or incredibly huge stars. And so, this mid-16, Galileo's fight with the Catholic Church was like 1633. He kind of backed the wrong horse because he was a fan of Copernicus. He didn't like Kepler at all. He didn't like Kepler's model. He really backed the wrong horse there. What pretty much everybody else backed, though, was Tycho. Again, because there was still those unanswered questions, right, about the problems with the moving Earth. Tycho seemed to be the best solution for them all. Modified it slightly, what they called the semi-Tychonic model. They said, okay, we'll let the Earth rotate too, so we don't have to have the stars rotating. And so at that point, that looked like that was the winner. Really, at the time Galileo was writing his treatise on the world systems, people were really thinking Tycho had it right, that was the right system. So he kind of was arguing against the straw man at that point when he argued against Ptolemy's model. Well, there's more. Kepler had some victories. Okay, there were observations that showed, observing the moons of Jupiter, that they obeyed Kepler's laws. That was a big, oh wow, yeah, who expected that? And this was a really big one too, the transit of Mercury. So in 1627, 4 years in advance, Kepler announced that Mercury would transit the sun, apparently go across its face, on November 7th, 1631. This was remarkable for two reasons. Not only had nobody ever predicted a transit before, nobody had ever even seen one before because they don't last very long and nobody was looking. So it's like, and here's Kepler saying, yeah, this is something you've never seen before. It's going to happen on this date. And Pierre Gassendi went to considerable effort to observe it and confirmed it on that day. So that was a big plus on the Kepler side. The next thing that happened was that we finally got some answers to some of those problems with the heliocentric model, Tycho's objections. Okay, so what about those star disks that indicate we have these huge stars? Well, Edmund Halley noted that when the moon passes in front of a star, if those disks were real and not some sort of optical illusion, you'd expect the brightness to not instantaneously blink out, but to sort of dim down over a short period of time. But no, they blink out instantly. And same thing when they reappear. William Herschel in 1805 noticed that the disk size that people think they're seeing through the telescope depends on the measurement conditions. If you put a smoked glass in front so it's not as bright, you get a smaller disk size. Again, evidence that maybe this is some optical effect, maybe this isn't real. And then finally, in 1835, George Airy, optics had advanced to the point where George Airy could actually put together an explanation of why the stars look bigger than they actually are. There's diffraction going on, even though their actual angular size would be way too small for you to see it. That image gets kind of sort of smeared out.
Is that diffraction with the atmosphere, or is that diffraction in the telescopes?
In the telescopes and the eyes, there's probably some of it in the atmosphere too. But even without the atmosphere, there's some of it in your eyes and in telescopes themselves. And the other thing that happened is in 1838, Frederick Bissell somebody finally measured actual parallax to a star, 61 Cygni. So notice this is way out there. This is a couple centuries later. It took a long time to really get this stuff, to really resolve all these issues. And that was a big shock, right? Because at that time, it's like, this is nearly 1 million times the Earth-Sun distance is how far away that star is. And 61 Cygni is one of the closer stars.
Wow.
It's not the very closest, but it's one of the closer ones. But the real knockout punch is something called stellar aberration. So in 1729, James Bradley was trying to measure parallax. A lot of astronomers have tried to measure it, and he kept on getting some very questionable results. He was trying to measure it for 2 stars, Gamma Draconis and 35 Camelopardalis, and he got some strange results. So this is sort of like showing the deviation over the year that he got. You expect a deviation if you got parallax, but this didn't fit parallax. The shape was wrong. The pattern didn't fit parallax. And so they tried to figure out what in the world is going on here. And they figured out that it was stellar aberration. So imagine that you're walking through the rain. Okay? And the rain is falling straight down. Okay? You start walking forward, and the rain now seems to be angling towards you. Okay? Now replace rain with starlight coming down, and an Earth moving through that light. That's what stellar aberration is about. So what you see here, this shows one way of it. Think of this, the star is actually in this direction. The light is coming down, the telescope moves forward with the Earth, and by the time it gets down to the eyepiece, that gives you, it looks like the star's over here. So there's a shift. And that shift changes over the year for all stars in a pattern that matches the Earth's orbit. And at that point, there is just absolutely no way that you can get that without the Earth moving. Okay?
That's a very small number, though, isn't it?
Yes, it's a small number. But it was one that they were able to measure in, this is 1729.
Ah.
Yeah. I mean, you needed a telescope to measure it. But yeah, and by the way, to make this logic work, you have to know how fast the speed of light is. Because that angle depends on the ratio between the speed of the Earth and the speed of light. But they had measured that in 1676 already.
Really? Prior to Einstein?
Oh yeah,
Long before.
yeah, a long time ago. A lot of different. I mean, that's a whole other discussion how they measured that. But that went way back, yeah. So finally, we've settled it. It's the sun's at the center. They're ellipses. They're not perfect circles. Yeah, but what's pushing the Earth around? We still haven't settled that one, right? So, we're going to finish here by what was missing is why this motion? Why these orbits? Okay, they figured out the shapes. They figured out it had to be going around the sun. But why? It kind of seems kind of arbitrary, right? What was the explanation? Okay. And so, in 1687, along came this long-haired hippie type by the name of Isaac Newton, Izzy to his friends, with a 3-volume page turner entitled Philosophiae Naturalis Principia Mathematica, which means Mathematical Principles of Natural Philosophy. I guess this was an early example of the importance of time reversal in physics or something. I don't know. Newton was English, so of course he wrote Principia Mathematica in Latin, which was the lingua franca of science at that time. And in this work, he set out a new framework for understanding motion. This was really the beginning of physics, I mean, the modern physics. And he came up with these laws of motion, and I'm not going to be able to get into exactly where they came from. A lot of this was based on a lot of work done by scientists in the previous century, Galileo and others. You know, you probably remember all the stories about dropping cannonballs and measuring pendulums and all that kind of stuff. So they'd figured out that, wait a minute, you know, there's a reason that things stop when you stop pushing them because of friction, and that absent frictions, things tend to keep on moving, and that's the Newton's first law of motion, inertia. A body at rest will remain at rest, and a body in motion will remain in motion unless it is acted upon by an external force. Okay. The second law of motion, I don't know how they all say one, sorry, is force equals mass times acceleration. The force acting on an object is equal to the mass of that object times its acceleration. This is actually a special case of this one, right? Because if your velocity is not changing, staying the same, then you have no acceleration. And that means no force. If you have no force, you have no acceleration, and so you keep on moving. This also sort of is implied by the whole idea that of relative motion that Galileo and others had worked out. That there is no absolute motion, they'd figured out, right? If we're in a boat and I see you going past me like this, I can't tell by any experiment that I could do within my room looking out the porthole whether I'm moving forward or you're moving backwards. Right? You may have noticed this in a train or in a car. You know, you see the other one moving, it's like, wait a minute, am I moving forward? Are they moving? What's going on? You know, you get a little confused there, especially if you're on a hill, right? And you see the other car moves forward, and you think, oh no, I'm sliding down the hill. You know. As long as it's uniform, smooth motion, you can't tell the difference. No, I have a demo here. Do a quick demonstration. So the third one you may have heard about before, you know, action and reaction. For every action, there is an equal and opposite reaction. So consider this ball. All right, we know that for its velocity to change, there has to be force acting on it. All right, wherever it went there. Now you saw it bounce off the wall. You know that when it hit the ball, it delivered a punch to the wall, a force to the wall. But it changed velocity. So there was a force acting back on it too. It was pushing on the wall, and the wall pushed back. That's why it changed velocity like that. Now the important thing here is that velocity has both a magnitude, how fast you're going, and a direction. Okay, so a velocity moving like this is a different velocity than moving through this because they've got a different direction, even if they're the same speed. An acceleration is any change of velocity. And so that acceleration can happen in the same direction you're going, like when you put your foot on the pedal of your car and accelerate forward. Or it can just mean that you change direction. That's also an acceleration because your velocity changed. And so force doesn't have to make you go faster or slower. It can just change your direction that you're moving at.
Depends on where you're measuring it from. At which angle it's being measured.
You will still, an acceleration you will still see, if it's not in the same direction as velocity, you'll still see it as a change in the direction regardless of where you're measuring it from. So that's basically what I was saying here. So if you think of this, for example, if this arrow here represents the velocity of something moving forward, and suppose, gravity is pulling it downwards, accelerating it downward. So suppose we have a small increment of time. We've got that constant acceleration downward from gravity, and it adds this much velocity. The new velocity is, you add the arrows together like that. So the new velocity is it's changed direction. It's actually, this length is a little bit larger, but it's also changed direction. So what we really see happening here is that it's curving around. And this was an insight that even before Newton, that Huygens worked out in 1659. He analyzed what happens with centrifugal, well, we say force and quotes, it's not really a force. Circular motion. Okay. Consider uniform circular motion like this. Okay. So the speed of this is pretty constant. I'm trying to make it constant. But the direction is changing all the time. Right? And you'll notice there's a tension in this string. There's a tension you can feel the tension in the string. It's constantly pulling that ball inwards. And that's the reason why it's changing direction. It's accelerating, there's a force pulling it inwards, but it never goes any faster. It just changes direction because of that. And that's what Huygens figured out. And that kind of fed into some of Newton's work. Let's just suppose we did a numerical simulation of this. So let's suppose we start off with a body that is in this velocity, and there's like a gravitational force or something pulling in this direction. After a small increment of time, its new velocity will be this. So I might simulate it by saying, let's just assume that the velocity stays the same for a small increment of time. And when it gets up to here, I'll plug in this new velocity and simulate it for another small time increment and try to figure out what its trajectory is going to be. So if we do that, well, my time step's too large. I don't actually get the right answer, because these are really big steps I'm taking here. But if I take smaller time steps, it starts to look more like, and I chose the starting velocity, by the way, to be just the right velocity to get a circle. But if I take really small time steps, I eventually get a circle there. Okay. Now, Newton...
So that's explaining how we're measuring orbit?
That explains a circular orbit. So this is a simple case of a simple circular orbit. But I could do the same thing with a non-circular orbit. So this is where it was moving at just the right speed to keep a circular orbit. If it had been going too fast, a little bit too fast, it would have got an ellipse. It would have gotten a little bit higher and come back around again. Okay. Now Newton, he didn't have, fast computers. He didn't have any computers at all. He didn't have this, do numerical simulation as an option. So what do you do when you don't have computers and you can't write a program to do this, all these calculations for you?
You are the computer.
Well, if you're Newton, you say, well, I guess I'll just have to invent a whole new field of mathematics to solve it for me. And that's what he did. He invented calculus, specifically Solus. And so using calculus, you can actually get formulas for what these orbits look like without having to do that numerical simulation. You get an exact answer in many cases. And that's the whole reason for the calculus, was so you could get those exact answers. And so when he explained this whole business of orbits, he used the idea of Newton's cannon. So suppose you have a really tall mountain and you shoot a cannonball out of it. And this was actually from a simulation that was online. And so this first one here is like you're shooting a cannon at 3,000 meters per second. This is 4,100 meters per second, 5,200 meters per second, and so forth. And you'll see that, what's happening, here's another way of seeing it, is that gravity is curving its path, and at some point, it's going faster and faster, and it's starting to curve just a little bit more than the curvature of the Earth. And then finally, the curvature is enough that it gets past the far side and keeps on going all the way back around. Now this isn't a perfect circle, it's a little bit closer here than it is here. That's a little bit of an ellipse. Go a little bit faster and eventually get a perfect circle if you want to.
So it's falling to the earth but missing, basically.
Yeah, throw yourself to the ground and miss, yeah. All right.
So what causes a satellite to re-enter Earth's orbit?
Air friction.
So
There is
they
a
are
very
being
little
affected
bit of,
by-
because a lot of these are, so this isn't a problem with the ones that are way out at the geostationary orbit, because they're way out there. They're thousands and thousands of miles away. But the low Earth orbit ones, there's just some very thin wisps of atmosphere that over time will slowly begin to degrade its orbit because of that. So the last piece of the puzzle here is Newton's law of gravitation. I'm sorry this is taking a while. We're almost done.
It's okay. This is awesome.
So he figured out he figured out gravity, at least the first attempt at gravity, that there's a force between any two bodies, a gravitational force. There's a gravitational force between me and that lamp. That's very small, and we don't normally notice this. And the gravitational force is directed towards each other, inwards. So I'm pulling the lamp towards me, and the lamp is pulling me towards it a little bit. And this formula gives the magnitude of that force. Now this G here is just a proportionality constant. It's a constant you have to determine empirically by doing experiments. But this is the mass of the first object times the mass of the second object. And r there is the distance between them, divided by r squared. Now this works mostly for points. Real objects aren't points. But it turns out that for spherically symmetric bodies, you do the math. Newton did the math. He did the calculus. Proved that for the spherically symmetric bodies, you could treat them as a point mass. Okay. So in our case, this r here, m1 would be like the Earth's mass. If we're trying to figure out, my weight, how hard the Earth is pulling on me, and how hard I'm pulling on the Earth, that this would be the mass of the Earth, this would be my mass, and this r here would be the distance to the center of the Earth, about 4,000 miles. Okay. Where did that come from? It just like it magically pulls us out of the air. Where did that come from? Well, actually, you can sort of reconstruct what he did. So, an experimental result from Galileo and other scientists was that gravitational acceleration of the Earth is the same for all bodies. The old dropping the cannonballs, one's twice as heavy as the other, but they still hit the Earth at the same time. The fact that it's the same, because force equals mass times acceleration, acceleration is the same, that means we've got to have this m2 in there for the body being pulled towards the Earth. Okay. But wait a minute, we've got that action-reaction, the forces are symmetrical, that I pull on the Earth just as hard as it pulls on me. And so that means we have to have m1 in there also, by the third law. We have to have both masses in there. So that gives us our m1 and m2. What about this one? What about the 1 over r squared? Where did that come from? Well, one way of seeing it, there's actually 3 different ways you can see it. The first way you might see it is just say, could this explain the orbit of the moon? And so if you figure gravitational acceleration here on the Earth, and you figure out what the orbital period of something just above the surface of the Earth would be, how fast it has to move to stay in a circular orbit, it works out to 84 minutes. Okay, and that's about the period of a really low satellite. Suppose the gravitational force didn't fall off with distance. It's kind of an absurd thought anyway, because it would mean that things are arbitrarily far away in the universe would be pulling on us, but suppose it was. Then the moon's orbit would be 11 hours. Okay, that number's wrong. Okay, let's let it fall off with distance. What if it falls off as 1 over r? So if you get twice as far away, the force is half as strong. You do the calculation, that says you hit moon orbits in 3.5 days. So you try the next thing. Let's try 1 over r squared. If you get twice as far away, the force is 4 times smaller, 1 over 2 squared. You do the calculation, 27.1 days. The actual orbital period of the moon, sidereal orbit, is 27.3 days. That's a little bit less than a month because the Earth has moved around the sun during that time, and so it has to go a little bit further around to make up the difference. The next argument you could use, Kepler's laws. If you're just looking at a circular orbit, then you can work out that for a circular orbit, the force that has to be pulling it in has to be proportional to r, the distance from the center, divided by the square of the period. But Kepler's third law tells us the square of the period is proportional to the cube of the distance. We plug it through there, we do some math, we get 1 over r squared. The third method is that if if you take all of Kepler's laws together, they tell you what the velocity of all the planets is at every point in their orbit and how fast they're going. And from that, you can figure out what their acceleration is, how their velocity is changing at time. And so again, they pulled out their calculus. Newton applied his magic weapon of calculus. And when he does that, he finds the acceleration is always in towards the sun, and it's proportional to 1 over r squared. So 3 different methods, they all give that the same thing. So it wasn't just pulled out of the air. It was actually by looking at all these, what you had to do to make it fit the observations. So what are the consequences of all this? Kepler's laws. Newton was able to derive them. They're not exactly true. They're an approximation. They're an approximation where you've got one body that's much more massive than the others. Okay, so that it doesn't move much. Like me and the Earth, right? I pull on the Earth, but it doesn't really move much. And the other approximation is that any other bodies in the system, that their pull, their gravitational pull, is small enough that it doesn't make much of a difference. That's not perfectly true, but as an approximation, it's like a first order approximation. Another consequence, because of that third law, the sun has to be at the center, simply because it's got most of the mass. So we've got these gravitational forces between things. The Earth is much more massive. It just doesn't move much. It turns out that from his formula, you can figure out the relative masses of different bodies by comparing orbital periods of their satellites. So if you want to know how massive the sun is compared to the Earth, you use those Kepler's laws, you use those formulas from the gravitational force, that Gm m1 m2 over r squared. You do that for the Earth, you plug in the Earth's period, you do it for the period of the moon around the Earth. The more massive the body is, the faster the rotation, the other body will orbit, and you can get their relative masses. And so you can figure out the sun is more than 300,000 times as massive as the Earth.
Is that how they're doing it for distant stars too?
Yeah, that's how they figure out for stars, is they look how fast, what kind of rotation they're seeing, the speed of rotation. And so this was actually the first interesting something, because, this is just from observation. You never went out there and scooped up a bit of star stuff, of sun stuff. But based on Newton's laws and these observations, you could already figure out that the density of the sun is about a quarter of the Earth's, 26%. So already you know that there's something different in their composition based on that. Same thing for Jupiter. You can look at how fast its moons go around it. You can compare that to how fast our moon goes around it. You can plug in the numbers, and you figure out, you've got the diameter of Jupiter, how much bigger it is, its volume. You figure out that its density is about 24% of the Earth's.
Its mass can be much greater, but its density is so much less that it doesn't affect its moons or its satellites.
That's really not going to make a difference. The density is not going to affect the moons. You can basically more or less treat it as a point, as far as the gravitational force is concerned. But it's the fact that if the Jupiter had the same density as the Earth, it would be more massive and its moons would move faster. Right? To be as dense as the Earth, because of its great size, Jupiter would have to be much more massive.
Yeah.
And you would notice that from the speed of its moons. And so, right off the bat, you know that Jupiter, its composition is very different from the Earth's. You haven't gone out there, you've never scooped up a piece of Jupiter and analyzed it. But you already know that it's about a quarter of the density of the Earth. And I think it's just amazing.
And it doesn't matter.
You're sitting here on the ground, and you know that Jupiter is much less dense than the Earth.
Yeah. And it doesn't matter how far its satellites are from its surface?
No. Well, I mean, if they're really, really close, the fact that Jupiter is a little bit flat might make a difference. But
Just
it's the first approximation.
Equatorial area. Yeah.
But I sort of left the best for last here, because up to this time, nobody expected the same laws to apply in the heavens as applied on the Earth. There was the physics of the Earth, and there was the physics of the skies. They were completely different things. No reason at all to expect them to have anything to do with each other. And suddenly Newton is saying, no, it's the same laws every place. Unification. Nobody expected that. That was a shock to everybody. The heavens, which had been thought of as this almost magical, mysterious place, now kind of prosaic, you know. It's just the same old stuff as going here on the earth, you know. And not quite so mysterious anymore. Okay. Now, despite all this, you know, Newton came up with all this by looking at the evidence and so forth, and came up with his laws. It's one thing to come up with an explanation after the fact. And yeah, it did fit well, but you can end up doing data mining where, like, yeah, you kind of told a just so story that just happened to fit this particular data set. What happens with future predictions? That's where you really know if you've got a good theory. Not just does it match the data that you already have, but does it predict things you hadn't seen before? Does it give the right answers for new situations that you've never encountered before? And so that's still a question. Is Newton really right? So what are some of the things that came out of that? Well, using Newton's laws and taking into account the pull of Jupiter and other planets, you get more accurate predictions of the motions of the planets that are better than Kepler's. One problem with Kepler's system was that it never quite fit very well for the moon. And it turns out that's because the moon is kind of got a far orbit from the Earth, and the sun, if you take into account the sun's gravity and the Earth's gravity together, then you get a much closer fit using Newton's laws. But one of the real victories was the story of Uranus and Neptune. See, Uranus was discovered in 1781, William Herschel. The first planet discovered in modern times. And orbital predictions for it, based on observations, were published in 1821. And these predictions were based on Newton's laws. And Uranus refused to follow the predictions. It was off a bit. There were some pretty substantial deviations. And so it was hypothesized that maybe there's another body out there that is perturbing it, that's pulling on it. That, you know, when it could be slowing it down by pulling it back, or another part of the orbit could be pulling it forward instead. And so two different astronomers, Adams and Verrier, sort of said, what would we have to account for these discrepancies? And they calculated, well, if we had a body of this particular mass, at this location, in this orbit, it would account for what we saw. And they published that in 1845, early 1846. And Neptune was discovered in 1846, where they said it was going to be, within a degree of position. So basically, astronomers looked where they told them to look, and they found it. And that was the big verification. And I guess the only last little bit of verification is, you know, Newton's claiming that everything pulls on everything else. But it's a small force. You know, it takes the entire mass of the Earth to get a sizable force pulling on me. Are we sure that's right? I mean, well, Cavendish in 1798 actually measured gravitational force in the laboratory. He set up this apparatus with lead spheres, a couple of very large fixed lead spheres, and some smaller lead spheres that were dangling from a very thin wire. Okay? Now, he was measuring a very small force, so he put this whole thing in a box, so there'd be no air currents or anything. And he put the box inside of his shed, so nothing would disturb it. And he didn't dare go in there and look at it himself. So he had a hole inside the shed, and he was off in a distance looking through a telescope. It's just all these things he had to do to even be able to measure this. You know, and so he's measuring the twisting force in that wire caused by the gravity. Very, very small force. It moved 1/6 of an inch.
Wow.
And he measured the gravitational force. And from that, he could then tell what the mass of the Earth was and its density, and then knew the density of everything else. He got a density that's about, something like 5 times the density of water. Rock is about 2.5 times the density of water. So right off the bat, they knew the Earth wasn't just a ball of rock, because it's too dense for that. All right, so everything works, great. You know, Newton's explaining everything, right? There was just one loose end, okay? Everything was looking great for Newton, except for this one little loose end, Mercury's orbit. So we've got this elliptical orbit for Mercury, except that there's this very slow drift in this perihelion. So this is greatly exaggerated here, but think in time it's slowly drifting like this. That's what precession is. Astronomers noted this. Nobody could explain it. Well, they could partially explain it. So applying Newton's laws, they could explain about half of that drift. But that precession was twice as large as Newton said it should be. What was the explanation? They waited, literally hundreds of years, and it wasn't until the early 20th century when the notorious womanizer Al Einstein came up with an explanation for what was going on. But that's a story for another day.